Good afternoon, everyone. Hey, good afternoon. And could you please press the thumbs up sign if you can hear me and you can see the screen with the IMath Webinar series and speakers. Okay, thank you very much. All right, so good afternoon, everyone, and welcome to the fourth webinar of the IMath Webinar series for this semester. I am Gino Angelo Velasco, the coordinator for research of the Institute. So for today's webinar, we will be having two speakers from the discrete geometry and combinatorics group and from the matrix analysis and linear algebra group. So please be reminded, please take note that this webinar is being recorded. Actually, it is being recorded right now. And it is being streamed live via YouTube, and the link will be posted on the official IMath Facebook page. Okay, so let us call on our first speaker. The first speaker for this webinar is Mr. Jomar Kevin Santa Ana. He is an instructor of the Institute of Mathematics and a member of the Matrix Analysis and Linear Algebra group. So today we'll be hearing his talk titled Sums of H self-adjoint, H skew-adjoint, and H unitary matrices. Okay, so let us all give Mr. Santa Ana a round of virtual applause. Kevin?
Hi, sir. Thank you po. At magandang hapon po sa inyong lahat.
Yes, good afternoon. Yes, you can share.
Yes po. Ayan, okay na po yung sharing, sir?
Yes, kita po namin. Salamat po.
Okay po. Okay, so again, magandang hapon po sa inyong lahat. I am Jomar Kevin Santa Ana, and today I will present some parts of my MS thesis, and the title of my presentation is The Sums of H self-adjoint, H skew-adjoint, and H unitary matrices. Okay, so we start with notation. We denote by Mn the set of all n by n matrices with entries from the field of complex numbers C. We denote by GLN the set of all non-singular matrices in Mn, and by C to the n, or just Cn, the set of n by 1 matrices with entries from C. Okay, so we start with the following definition of an indefinite inner product. And so a function from Cn cross Cn to C is said to be an indefinite inner product of Cn if the following conditions are satisfied. So first, the function should be linear on the first component. The second property is what we call the Hermitian property. And the third one is what we call the non-degeneracy property. So I know most of you is not familiar with the indefinite inner product. Most of us siguro familiar sa standard inner product. So what's the difference between the indefinite inner product and the standard inner product? So one can show that an indefinite inner product will satisfy all of the actions on the definition of a standard inner product, except for non-negativity and positivity. So thus, the indefinite inner product is a natural generalization of the standard inner product. So yun yung difference ng dalawa. Also, one can show that every indefinite inner product on Cn arises as y star hx. Ibig sabihin, we can always find a Hermitian non-singular matrix H such that the indefinite inner product of x and y equals y star hx. So itong indefinite inner product na ito, gagamitin natin yan to define what we call the H adjoint of a matrix A. So suppose A is a square matrix, then the H adjoint of A is the unique n by n matrix denoted by A to the H, which satisfies the following equation. So the indefinite inner product of Ax and y equals the indefinite inner product of x and A to the H times y for all x and y. And one can show that equation number 2 is true if and only if a to the h equals h inverse a star h. So we now have a value for the h adjoint of a matrix A. Okay. And gagamitin natin itong definition ng h adjoint to define some special types of matrices. And here they are. So we let A to be an arbitrary square matrix. We say that A is H self-adjoint if A to the H equals A. H skew adjoint if A to the H equals minus A. And H unitary if A to the H times A is the identity matrix. So we can say na itong tatlong matrices na ito, tatlong types ng matrices na ito are defined from the indefinite inner product. Kasi kinuha natin ito from the H adjoint, tapos yung H adjoint kinuha natin din sa indefinite inner product. Okay. So recall na ito yung value for A to the H na sinabi natin kanina. It is equal to H inverse A star H. So if we let H to be the identity matrix, so this is equal to I times A star times H. Therefore, A to the H equals A star. So ano mangyayari kapag we let H to be the identity matrix? H sub-adjoint, H skew-adjoint, and H unitary matrices are just the usual Hermitian, skew-Hermitian, and unitary matrices na alam natin. So we can view these matrices as generalizations of the Hermitian, skew-Hermitian, and unitary matrices. Okay. So for today, we are interested in the sums of H of adjoint, H skew adjoint, and H unitary matrices. So gusto natin masulat ang isang matrix as a sum of these special types of matrices. No? So di-discuss natin yung iba't ibang combination nitong tatlong ito. So itong susunod, ito yung mga trivial cases. So we let A to be an arbitrary square matrix. So A is a sum of two H self-adjoint matrices if and only if A is H self-adjoint. So ito, trivial lang siya. Madali lang siyang pakita. Same with the second one. A is a sum of two H skew-adjoint matrices if and only if A is H skew-adjoint. Okay, for number 3, every matrix A can be written as a sum of an H self-adjoint and an H skew-adjoint matrix. Indeed, we can write A as this sum, wherein this matrix 1/2 times A plus A to the H, we can check that this is H self-adjoint, while the other one is H skew-adjoint. So itong tatlong ito, madali lang silang ipakita. Actually, ano sila, properties sila ng Hermitian at skew-Hermitian matrices na na-carry over dun sa kanilang mga generalizations sa H self-adjoint and H skew-adjoint matrices. Okay, so ano pang kulang? Meron pa tayong natitira na medyo mahirap ipakita. So, yung goal ng presentation natin is to determine sufficient conditions for an arbitrary square matrix to be expressed as a sum of number 1, an H of adjoint and an H unitary matrix, or as a sum of an H skew adjoint and an H unitary matrix. Actually, there's a third one. Express the matrix as a sum of two H unitary matrices. Pero pag-focus na tayo sa presentation ko for today dito sa dalawang ito due to time constraints. Okay. So we define the following n by n matrix Q sub n, wherein we have positive ones on the antidiagonal and is 0 elsewhere. This matrix is what we call the SIP matrix of size n, or the standard involuntary permutation. Sometimes it's called the backward identity matrix. So some properties of Q sub n, as we can all see, Q sub n is symmetric. If you take the square of Q sub n, you will get the identity matrix. And so the inverse of Q sub n is itself. As for the eigenvalues, if n is even, then Qn is similar to this direct sum. Ibig sabihin, Q sub n has n over 2 positive 1 eigenvalues, and it has n over 2 negative 1 eigenvalues. If n is even. If n is odd, ito naman yung Qn is similar to this matrix, so therefore we have n plus 1 over 2 positive 1 eigenvalues, and n minus 1 over 2 negative 1 eigenvalues. Okay. So just to give you an idea, no, anong itsura ng mga H-adjoint matrices. So we give some examples here. Observe that for any positive integer k and complex number lambda. So i-compute natin yung product ng dalawang matrices na ito. So this is Q sub k, this is jk of lambda. The product is this matrix, and this is precisely jk of lambda transpose times Q sub k. So we can conclude that jk of lambda equals Q sub k inverse jk of lambda transpose times Q sub k. Okay, so ito yun, sinulat ko ulit dito. This is true for any positive integer k and complex number lambda. And sinulat ko ulit dito yung definition ng yung value natin for a to the h. No? This is equal to h inverse h star h. So here are some examples of h sub-adjoint matrices where yung h natin ay q sub n. So number one, if lambda is real, what can we say about jk of lambda transpose? So yung mga entries ng jk of lambda, lahat yan real na yan, no? Ibig sabihin, yung conjugate ng matrix na ito ay equal sa sarili niya. Therefore, jk of lambda transpose equals jk of lambda star. At anong sinasabi natin dito? Qk inverse times jk of lambda star times q sub k equal siya sa jk of lambda. But this is equal to jk of lambda raised to q sub k based on the definition. So therefore, we conclude that if lambda is real, jk of lambda is q sub k self-adjoint for any positive integer k. Okay, so kung hindi real si lambda, hindi ito totoo, no? So next example, for any positive integer k and complex number lambda, so compute natin ito, jk of lambda plus jk of lambda bar raised to q sub 2k. So we use the definition. So this is equal to q sub 2k inverse times the conjugate transpose of this matrix. So ito yon times another q sub 2k. Then by direct computation, we will get this matrix. And this is precisely jk of lambda plus jk of lambda bar. So notice that this is exactly equal to this matrix, no? Yung nasa loob ng parentheses. So therefore, we conclude that jk of lambda plus jk of lambda bar is q sub 2k self-adjoint for all lambda in C and for all positive integer k. Okay, so now, simulan na natin yung pag-prove dun sa goals natin. No? We start with the following lemma. If A is H self-adjoint and P is non-singular, then P inverse AP is P star HP self-adjoint. So this lemma shows that an H self-adjoint matrix A is invariant under simultaneous similarity of A and congruence of H. What else? This also allows us to study the properties of H self-adjoint matrices in the context of a canonical form. Kasi mahirap i-prove yung goals natin using an arbitrary square matrix A. So what we want is to find a canonical form para yun na lang yung gagamitin natin sa proof, no? And this lemma tells us na pwede natin gawin yun. Why? Because if we have an H self-adjoint matrix A, then we know that P inverse AP is P star HP self-adjoint. So ito na lang yung gagamitin natin sa proof. So ito yung ibig sabihin na si A ay invariant under simultaneous similarity of A and congruence sa H. Because A is similar to this matrix and H is star congruent to P star HP. So ang tanong ngayon, meron ba tayo makukuha canonical form for an H self-adjoint matrix? And it turns out, yes, we have a canonical form for H self-adjoint matrices. This theorem is from the textbook written by Gobert et al. In 2005. Let A be H self-adjoint. Then there exists a matrix P, non-singular, such that A is similar to J, and H is star congruent to H epsilon via the matrix P. So ano itsura ni J tsaka ni H epsilon? Si J is just a direct sum of these Jordan blocks wherein yung lambda 1 up to lambda sub alpha are the real eigenvalues of A. So ito yung mga Jordan blocks corresponding to these real eigenvalues. Okay? And lambda sub alpha plus 1 up to lambda beta are the non-real eigenvalues of A with positive imaginary parts. So, sinasabing dito sa J, the Jordan blocks corresponding to the non-real eigenvalues of A come in pairs. So, ito yung Jordan block for lambda sub alpha plus 1 and so on hanggang sa lambda beta. So, this is J. Ano naman yung itsura ng H epsilon? So, this is H epsilon. Notice that H epsilon is partition conformal to J. So, yung mga Jordan blocks corresponding to the real eigenvalues, ito yung katumbas nila na blocks dito kay H epsilon. Similarly, sa mga non-real eigenvalues, ito yung mga katumbas nila. Tapos, notice that there are coefficients here, no? And this set, the set epsilon is an ordered set of signs plus or minus 1. So the values of epsilon sub 1 up to epsilon sub alpha are just positive or negative 1. And it is uniquely determined by A and H up to permutation of signs corresponding to equal Jordan blocks. So kahit na ano makuha natin P, dapat same pa rin yung epsilon because epsilon is dependent on A and H only. Okay. So now that we have the canonical form, so start na tayo dun sa actual proving ng goal natin. So we have here this proposition, let A be H of adjoint. Then we can write A as the sum x plus x to the H for some H unitary matrix X. If and only if A squared minus 4i has an H skew adjoint square root in C of A. Where in C of A, we call this the centralizer of A. It is the set of all matrices B such that B commutes with A. So this proposition gives us necessary and sufficient conditions for an arbitrary H of adjoint A to be written as x plus x to the H for some H unitary matrix X. So bakit tayo interested dito sa sum form na ito? Mamaya makikita natin bakit siya necessary sa ating goals. So for now, yan, meron tayong conditions, necessary and sufficient conditions para masulat si A as x plus x to the H. Okay. So, we show some sketch of the proof, pero backward direction lang. So, suppose y is an H skew adjoint square root of A squared minus 4i in the centralizer of A. Okay. So, take x to be 1/2 times A plus y. At ano ipapakita natin? We show that x is H unitary and we show that x plus x to the H equals A. Okay, so we compute for x times x to the H. So x to the H, we can distribute H to A and Y. So A to the H plus Y to the H. But A to the H equals A because A is H of adjoint. And Y to the H equals minus A because Y is H skew adjoint. So ito yung product niyan. Then simplifying this, we get 1/4 times A squared minus Y squared. But since y is the square root of A squared minus 4i, this is equal to this matrix, and then eventually we will get in. So we have shown that x is H unitary. So next, we compute for x plus x to the H. Yan, direct computation lang. Again, A to the H equals sa A, and Y to the H equals sa negative Y, since A is H of adjoint, Y is H skew adjoint. So eventually, we will get A. Okay. So maganda sana tong proposition na to. Pero ang problema dito, it's not easy to check right away if the matrix A squared minus 4i has an H skew adjoint square root in the centralizer of A. So syempre gusto natin conditions, so madali lang i-check. Kaya meron pa tayong susunod theorem. This is actually the main theorem of the presentation. So we let A to be H of adjoint. At suppose this is the canonical forms of A and H respectively. So isulat natin siya as this direct sum where A and J sub lambda is the Jordan block corresponding to the eigenvalue lambda. Okay. Suppose the following hold. Okay, so number 1, if lambda squared is greater than 4, at kung yung itsura ni J lambda at ni H lambda ay ito, ibig sabihin si J lambda, direct sum siya ng mga pairs of Jordan blocks na magkakasize. Tapos ganun din si H sub lambda, no? Pares-pares siya for some epsilon I1, epsilon I2. for some positive integer p. Kapag ganyan daw yung itsura, tapos si lambda squared is greater than 4, then epsilon I1 times epsilon I2 should be equal to negative 1 for all I. So that's the first condition. Next condition, if lambda equals plus or minus 2, and yung itsura naman ng canonical form natin, ganito. So si J sub lambda, well, direct sum lang siya ng mga Jordan blocks, no? Corresponding to lambda. Si A sub lambda, ganun din. Direct sum lang siya ng mga P sub K. Pero may extra conditions tayo. Dapat yung mga subscripts natin decreasing. Also, dapat the difference between K sub I and K sub I plus 1 is either 0 or 1. Anong ibig sabihin nun? Kapag in-expand mo itong yung direct sum ni J K sub I of lambda, yung una at yung pangalawa, dapat either pareho sila ng size or mas mataas na isa yung size ng pangalawa kaysa dun sa una. Same with the third and fourth, fifth and sixth, and so on. So this is, yun yung ibig sabihin nito, no? And then lastly, what if P is odd? Ibig sabihin, magkakaroon tayo ng extra Jordan block sa dulo. So if that's the case, wala siyang kapares, K sub P should be equal to 1. Ibig sabihin, 1 by 1 lang yung Jordan block na yan sa dulo. So if that's the case, then ito yung conclusion natin. Dapat yung product ni epsilon I and epsilon I plus 1 is either positive 1 or negative 1. If the difference of K sub I and K sub I plus 1 is 1 and lambda equals negative 2, dapat negative 1 siya. If the difference of K sub I and K sub I plus 1 is 1, pero ang lambda natin ay positive 2, negative 1. Pero kung ang difference ni K sub I at ni K sub I plus 1 is 0, negative 1 din siya. Sabi natin, difference ni K sub I and K sub I plus 1, either 0 or 1 lang naman. So that's the second condition. Anong conclusion natin? Then A can be written as the sum x plus x to the h for some h unitary matrix x. Okay. So this is the outline of the proof. First, we assume that A and H are given by their respective canonical forms. Bakit natin pwedeng gawin yon? So again, these are the canonical forms for A and H, no? So recall lang tayo. Ito yung gusto natin. We want to write A as the sum x plus x to the h for some h unitary matrix x. Pero according to this lemma, this is true if and only if there exists for any non-singular matrix P, there is a P star H P unitary Y such that P inverse AP equals Y plus Y raised to P star HP. Pero sabi natin, there's a theorem on the canonical forms. There exists a non-singular matrix P such that A is similar to J and H is star congruent to H epsilon. So we can take that matrix P para sabihin na si P inverse AP equal siya sa J and P star HP equal na siya sa H epsilon. Okay. So now, our problem is reduced to finding an H epsilon unitary matrix Y such that J equals Y plus Y raised to H epsilon. And this is so much easier now because right now we are dealing with the canonical forms instead of just an arbitrary square matrix A. So na-reduce natin yung problem natin. Okay, next step. Divide the proof into cases, each of which considers Jordan blocks from the canonical form of A. Okay. So ito ulit yung canonical form ni A, no? So hahatiin natin ito cases para ma-consider natin lahat ng Jordan blocks na nandito sa canonical form niya. So for case 1, consider natin yung mga lambda na non-real. So ano yung Jordan blocks corresponding to lambda? Ganito yung itsura niya. So this case will cover these Jordan blocks hanggang doon sa dulo. So H lambda here equals Q sub 2K. Ito yun. Maka-cover niya itong mga ito. So that's case 1. Case 2, we consider the case when lambda is real and lambda squared is less than 4. So anong itsura ng Jordan block niya? Ganito, no? JK of lambda. And then H lambda equals epsilon P sub K. For the third case, we consider the case when lambda is real, but lambda squared is greater than 4. Pero meron tayong condition, the first condition of the theorem, sinamahan natin siya ng condition na dapat si J lambda ay equal sa this direct sum, no? Dapat pares-pares yung summands. Same with H sub lambda. So that's case 3 natin. And the last case number 4, when lambda equals plus or minus 2, we consider this as direct sum. Saka ito sa H lambda, ito siya. Wherein, ito yung second condition natin. Dapat decreasing yung mga subscripts. Tapos dapat yung difference ng K sub I and K sub I plus 1, either 0 or 1 lang. And if P's odd, then yung pinakadulong Jordan block dapat 1 by 1 lang. So that's case 4. So what do we do to each case? We show that the Jordan blocks from each case can be written as a sum y plus y to the m. Ito yung, oops, sorry po. Wala yung sharing. Start ko lang po ulit. Ayan, sorry po. So again, so for the third step, we show that the Jordan blocks from each case can be written as a sum y plus y to the m for some m unitary matrix. So ito yung desired sum form natin kanina pa na pinag-uusapan natin. Tapos gagamitin natin yung previous proposition to show this. So ito yung previous proposition, recall lang natin. Ayan. Tapos if mapakita natin na bawat Jordan block from each case, sum na siya nito, sum form natin. Anong mangyayari? We will use this lemma. So basahin natin yung lemma na to. If A is just a direct sum of matrices A sub I, and H is non-singular Hermitian and is partition conformal to A, tapos, suppose yung each A sub I can be written as X sub I plus X sub I raised to H sub I for some H sub I unitary X sub I, then the whole matrix A can be written as this desired sum form. So, dun sa step 3 natin kanina sa outline of the proof, napakita natin na lahat ng Jordan blocks nasulat natin as this desired sum form. So eventually, the whole matrix A will be written as X plus X to the H for some H unitary X. And that ends the outline of the proof. Okay. So yun yung main theorem natin simply because the following corollaries magdidepende yan sa main theorem natin. So for the first corollary, so ito na yung sasagot din sa first goal natin. So let A be an arbitrary square matrix. Suppose J and H epsilon are the canonical forms of A plus A to the H and H, where J sub lambda is the direct sum of all Jordan blocks of A plus A to the H corresponding to the eigenvalue lambda. And suppose the following hold. For number 1, if lambda squared is greater than 4, and the canonical form is of this form, the conclusion is epsilon I1 times epsilon I2 equals -1 for all I. And notice, ito mismo yung condition natin, yung first condition natin from the previous theorem. The only difference is that the lambda here is an eigenvalue of A plus A to the H. Dun sa main theorem natin, lambda is assumed to be an eigenvalue of A. Okay. So for the second condition, ganun din. Same din siya dun sa condition from the previous theorem. But again, the difference is this. Lambda is an eigenvalue of A plus A to the H, not A. Okay, so what's the conclusion? We can write A as a sum of an H unitary X and H skew adjoint 1. So to prove this, take note that the matrix A plus A to the H is always H self-adjoint for all A and for all H. So, by the previous theorem, dun sa main theorem natin, we can write A plus A to the H as X plus X to the H, where X is H unitary. And then, manipulating this equation, we will get this. A minus X equals X to the H minus A to the H. But this matrix is equal to X minus A raised to H. Therefore, we conclude that A minus X is H skew adjoint. And therefore, A equals X is H unitary, plus A minus X is H skew adjoint. And we're done. Okay, so last two corollaries. So these two corollaries take care of the second goal natin. No? So let A be H skew adjoint. Tapos ito yung canonical forms, the A and H. Isulat natin as the direct sum of J lambda and the direct sum of H lambda, where J lambda is the direct sum of all Jordan blocks of A corresponding to the eigenvalue lambda. First condition, if lambda equals bi for some real number b, such that lambda squared is greater than 4 at j lambda and h lambda, ito yung itsura niya for some positive integer p. The conclusion is the product of epsilon i1 and epsilon i2 is -1. So again, take note, halos similar lang ito dun sa condition, dun sa main theorem. The only difference is that yung lambda natin iba. Siyempre, we are dealing now with HQ adjoint matrices. So iba yung itsura ng eigenvalues ni HQ adjoint kaysa sa mga eigenvalues ni H of adjoint matrices.
Jomar, parang may typo ka dyan.
Yes, ma'am?
Kasi hindi ba lambda squared is going to be negative if it is pure imaginary?
Opo, sorry. I think yung mga susunod ganun din yung mga ma'am, hindi po kasi yung B naman natin pwedeng naging sorry. Tama po, ma'am. So, typo.
Hindi ba less than 4?
Dapat less than 4. Sorry po. Ayun. Thank you po, ma'am, sa pag-point out. Tama, kasi lambda equals bi. So if we square lambda, it should be always negative. Okay. So for number 2, second condition, if lambda equals plus or minus 2i, the extra conditions are this. Pareho lang din dun sa main theorem natin. Dapat decreasing yung mga subscripts and so on. Then the conclusion is that the product of epsilon sub I and epsilon I plus 1 is either positive 1 or negative 1 based on these conditions. And then the conclusion is that we can write A as x minus x to the h. So minus po ito. So magkaiba siya dun sa main theorem. And then as a corollary to this corollary, ito na yung second goal natin. So we have an arbitrary square matrix A. Suppose J and H epsilon are the canonical forms of A minus A to the H and H. And lambda is an eigenvalue of A minus A to the H. So suppose the following conditions hold. Ayan, sorry, typo rin po ito, kagaya sa kanina. The same conditions, ang difference po nito from the previous corollary is that lambda here is an eigenvalue of A minus A to the H. So the conclusion is that we can write A as a sum of an H unitary and an H self-adjoint matrix. So to prove this, take note that A minus A to the H is always H skew adjoint for all A and for all H. So using the previous corollary, we can write this as this difference, x minus x to the H. So manipulating this equation, this is equal to this is equivalent to A minus x equals A to the H minus x to the H. Pero ito pwede natin isulat as A minus x to the H. So therefore, we conclude that A minus x is H self-adjoint, pero x here is H unitary. Yan. Masusulat natin si A as a sum of an H unitary and an H self-adjoint matrix. And there, that ends my presentation. Salamat po sa pakikinig.
Thank you, Kevin, for your talk. Let us all give drummer Kevin Santa Ana a warm round of virtual applause. Okay. Siguro share mo rin muna ulit yung slide just in case meron tayong question. Okay, so the floor is now open for questions from the audience. So you can type your questions in the chat box, or you can raise your hand and unmute so that you can ask your questions live. So Jomar, general question. So ito may question dito. Is the decomposition unit?
The decomposition unit. Balik po tayo dito, Yan, ito po. Hindi po siya tama ba? Unique po siya, sir. Kasi ang mangyayari. Babalik po tayo dito sa sa main theorem natin. Ayan. So, dito po sa sorry, corollary pa ito. Ito po. So dito po sa theorem, di ba, meron tayong conditions para masulat ito, no? X plus x to the h. Pero, ito kasi nanggaling siya dun sa proposition. Tapos sa proposition po naman, ito yung, yung pinili natin na x such that this is true. So, kung hindi naman po unique yung yung makukuha natin na h squared and square root ni a squared minus 4i. So, dito sa proof natin, tinake natin yung x to be 1/2 times a plus y. So, since hindi po unique si y, hindi magiging unique si x. And then, following this sa main theorem, hindi po siya magiging unique. Yun po yung answer.
Okay, thank you. Do we have any other question? So yung mga results ba dito, ano din siya? Parang generalized din siya or kumbaga mako-compare din siya sa results kapag ang case natin ay sa usual na self-adjoint or skew-adjoint unitary yung ating matrix. So yung mga conditions, for example, ma-relate ba siya like generalization or
Yes po, sir. Lahat naman po ng notion natin, generalized po siya dun sa usual Hermitian and skew-Hermitian. So mag-apply din po dapat ito dun sa mga yan. If we take H to be the identity matrix, lahat po dapat totoo pa rin.
we have any other question? And okay, so kung wala po tayong question, meron po tayong question dito from Dr. Kaalim. Hello, Nathan. Ano hindi pa nagagawa?
Ayan po, marami po sir. Kasi kung napansin niyo po dun sa main theorem ko, this theorem only gives us sufficient conditions para masulat si A as x plus x to the h. So yung goal ko po sana dun sa MS thesis, syempre gusto natin necessary and sufficient. So sa ngayon, yung, sufficient pa lang po itong nandito. So yung necessary kulang pa. Hindi siya ganun kasimple kasi kung matatandaan niyo po dito sa outline, ginamitan ko po siya nitong lemma. Sandali lang po ha. Ito po. So, etong lemma na to tells us na kapag yung each Jordan block na nasulat po natin dito sa sum form na ito, and then automatic yung A natin, masusulat na natin as x plus x to the h. Pero it turns out yung converse po nito hindi totoo. Meron pa tayong extra condition na dapat dapat magkakaiba sila ng eigenvalue. So, dahil dun sa reason na yon, hindi natin basta-basta magagamit yung lemma at hindi madaling ipakita yung kabilang direction. So, ang ginagawa ko po so far, pero hindi ko pa natatapos. Yes po, sir?
Yung counterexample, Jomar.
Ano po yan? Sorry?
Yung sabi mo about the converse, the other direction.
Po.
You have an example?
Walang example. Paano pong example? Parang
Can you just repeat what you just... I missed the one you
okay,
said,
po.
the other direction.
So bali dito po sa proof, since bawat Jordan block mapapakita natin na masusulat natin siya as this desired sum form using this lemma, since yung 'di ba inassume po natin yung A is the canonical form na lang. So yung canonical forms natin direct sum lang naman po siya ng mga Jordan blocks. So if each Jordan block masusulat natin as this desired sum form using this lemma, yung mismong A natin masusulat po natin as x plus x to the h. Ang problema po dito sa lemma na ito, hindi po, the converse is not true, no? So, hindi po porket masusulat natin si A as x plus x to the h, bawat samad na niya ay masusulat na natin as x of I plus x of I raised to h of I. So, magkakaproblema po tayo dito. So, dun sa paper ko po nun, meron tayong extra condition para masatisfy yung covalent direction. Dapat each x of I distinct yung mga eigenvalues po nila. So, yun. Kaya mahirap ipakita yung kabilang direction. So, ang attempt ko po so far is hindi ito, pero ginagamit ko po yung proposition. So, magsusuppose ako na si A, yung matrix natin, ay merong, tapos kukunin ko yung A squared minus 4i, meron siyang h squared and square root in the centralizer of A. Tapos, at some point, dapat marirelate ko po siya dun sa sa mga epsilons kasi yun po yung conditions dito eh. Ito po. Yan. Sa mga epsilons natin. So, yun yung attempt so far. Pero hindi pa po hindi ko pa po siya natatapos gawin.
Okay na po ba, Dr. Kaalim?
Pwede ko bang i-follow up lang? So, so yun yung nagawa mo na for the other direction of this theorem for the then if part. Pabaliktad.
Ano po yung tanong? Sorry, sir.
Na-miss ko lang yung last sentence mo. You said
Bali, so far, ang attempt ko po is parang ipakita yung kabilang direction using the proposition. Nasaan yung proposition ulit? Wherein, I assume that the matrix has yung a squared minus 4. Halimbawa, meron tayong a, tapos kunin ko yung a squared minus 4i nun. As I assume that a squared minus 4i has an joint square root in the centralizer of a. So, meron naman po akong form na nakukuha na masasatisfy niyo yung condition na yon. Tapos, pag may nakuha na po akong form ng matrix, so far, ang attempt ko po ay parang humanap ng parang sort of contradiction para yung epsilon, para ma-limit yung choice natin ng epsilon. Kasi dito po sa theorem, di ba, ang mga outcomes natin ay in terms of the products of epsilons. So, dun sa attempt ko po, yan, meron akong form ng matrix, tapos hahanap ako ng contradiction na baka may cases na bawal pala ito dahil ganito, ganyan. Sorry, malabo po ba?
Thank you. Sorry.
Salamat po, sir.
Okay, so thank you very much. So thank you, Dr. Kaalim, for the question. So kung wala na po tayong question, pasalamatan po ulit natin si Mr. Jomar Kevin Santa Ana for giving us that nice talk. And in a sense, yung perspectives din for future work. So bigyan po natin siya ng virtual applause. Thank you, Kevin.
Thank you po, sir. Thank you po, everyone.
Okay, so now we'll go on a short break. So we'll go on a 3-minute break and then we will hear the talk from Dr. Amat. Okay, so again, good afternoon and welcome back to the IMath Webinar series. Our next speaker is Dr. Maria Carmen V. Amara, the Discrete Geometry and Combinatorics Group. She's an associate professor of the Institute of Mathematics, and today she'll present her work titled Abstract Regular Polytopes from Orthogonal Groups. So let us all welcome Maria Carmen V. Amara.
Good afternoon. Naririnig niyo po ba ako?
Yes po.
Okay, so good afternoon. What I will present today is joint work with Michael Judici of the University of Western Australia. This is a bit of old unfinished work, emphasis on unfinished, from my first visit here in 2018-2019. So the talk will consist mostly of a lot of description of the background and a couple of slides on what we have done, our very partial results, and what we are still hoping to do. So again, I apologize, this is very unfinished work, but I will try to present the background in as accessible a way as possible para lang maintindihan ninyo kung ano yung idea, kung ano yung goal namin. So we shall begin with a brief introduction of the idea of abstract polytopes at yung connection nito sa more classical polytopes that we are familiar with. So how do we extract the, how do we transition from classical polytopes, yung geometric polytopes, to abstract polytopes? And then I will introduce an object called string C groups and explain the connection of string C groups with abstract polytopes. And then we shall give a bit of background on the orthogonal groups, which is the special case that Michael and I were focusing on. And then I will show you a few results from what we are doing. So let us consider a triangle. A triangle, we know that to be a polygon, parang a two-dimensional object. So let's say that our triangle has vertices A, B, and C. Now, we know that this triangle has 3 vertices and 3 edges. Let us call each edge consists of 2 vertices. Meron tayong AB, AC, and BC. Now, we shall be interested in the relationship of these objects, the vertices and the edges, to each other. So we shall say that a vertex and an edge are adjacent exactly when the edge contains the vertex. Using that incidence relation, we can then draw a diagram illustrating the relationship among the vertices and the edges. So if we list the vertices on one level, yung pinakababa, and the edges on the second level, then we can connect a vertex and an edge whenever the vertex is contained in the edge, whenever they are adjacent. And then we can consider the entire triangle itself to be another object. So all of these edges, each of these edges is contained in the triangle ABC. So may edge tayo connecting each edge with the triangle. So we are interested in this diagram illustrating the relationships between the elements, the objects that make up our triangle. We can also do that to objects in higher dimensions. So a regular tetrahedron is a polyhedron, okay, parang 3-dimensional analog ng polygon. Let's say that our tetrahedron has vertices A, B, C, and D. So ano-ano yung mga parts ng isang tetrahedron? Apart from the vertices, we can talk about the edges. So meron tayong edges. Each edge consists of 2 vertices. Apart from the edges, we also have faces. yung triangles that make up each face of the tetrahedron. So, tatlo yung types ng objects. May vertices, 4 na vertices. And then we have 6 edges. And then we have 4 faces. Each face is a triangle. It consists of 3 vertices. So, how are these objects related to each other? So, vertices are contained in the edges. The edges are contained in the faces. And the faces are contained in the whole tetrahedron. So we can again draw a diagram illustrating that relationship among any two of these objects. So mas complicated ng konti ang ating diagram because we have more objects. But again, this illustrates incidence, the incidence relation in this geometric object. So when we are studying abstract polytopes, we are not interested in the original, in this object. Rather, we are interested in this diagram, yung relationships among the parts of our geometric object. Now, let's go back to the diagram for the triangle. We can think of ABC as a set consisting of 3 objects, and the pairs AB, AC, BC, and the singletons A, B, and C as subsets of this 3-element set. So, ano yung ini-illustrate na to? Ini-illustrate na to yung subset, lattice of subsets ng set natin na ABC. What is missing here is the empty set. So, if we add the empty set, then we have here the full lattice of subsets of the 3-element set ABC. Now, we shall we shall define a flag in the triangle, a sequence of objects starting with the null set, and then we have a vertex, an edge in the triangle itself, satisfying the condition that the vertex is contained in the edge. We know that the null set is always contained in a 1-element subset, and the edge is always contained in the triangle. So, ito ay sequence of 4 objects, each of which is incident to the next. Now, what are the flags in this triangle? There will be 6 flags in this triangle. Yung unang flag ay yung null set, yung vertex A, yung edge AB, and yung triangle ABC. And then you can check that you have 5 other flags. So a flag in a triangle is a maximal chain of adjacent objects from the bottom object, yung null set, to the topmost going up, okay? We can do the same for the tetrahedron. So again, if we look at A, B, C, D, we can look at this, we can view this as a set of 4 elements. And if you examine these objects, these also correspond to subsets of the set of 4 elements A, B, C, D. So ang kulang dyan ay yung null set. If we add the null set, then we have this diagram of this lattice of subsets. We can also talk about flags in the tetrahedron. Mas i-extend lang natin yung definition ng flag for a triangle. So you take a sequence of 5 objects. Well, the first one is the null set, and the last one will be, this should be ABCD, is the tetrahedron itself. And then in between, we have a vertex, an edge, and a face, such that the vertex is contained in the edge is contained in the face. So that is yung succeeding, yung magkakasunod na element sa ating sequence, dapat sila ay incident to each other in this diagram. So there are, there are typos here. This should be my ABCD dito sa dulo. So here are examples of flags. So we have here the null set, the vertex A, the edge AB, the triangle ABC, and dapat may kasama sa dulo the tetrahedron ABCD. So those are flags. So again, we shall be interested in studying, when we study the tetrahedron as a polytope, We will not look at the geometric object itself. Rather, we will look at diagrams. At this diagram, we are interested in the relationships, in the objects that make up the tetrahedron, the parts of the tetrahedron, and the relationships of those parts to each other, yung incidence relationship. Now, so yan ang motivation for the definition of an abstract polytope P of rank n is an integer greater than or equal to -1. So this is also called an abstract n polytope. This is a partially ordered set. Pag sinabing partially ordered set, ano yung nasasatisfy? Nasasatisfy ang anti-symmetry and transitivity. So in addition to that, so the elements of this partially ordered set or of this poset are called faces. So yung vertex, yung edge, lahat sila tatawagin nating faces. It doesn't matter what dimension they are. Even the null set will be considered a face. Even the polytope itself will be considered a face. We have 4 conditions that should be satisfied. The first condition, P1, is that our poset must contain a least face, which we denote F subscript -1, and a greatest face, which we call F subscript n. Second, so yung F subscript -1, ito yung null set natin. Yung greatest face natin, yung F subscript n, ito yung polytope itself. Second, each flag, so a flag is a maximal chain or a maximal totally ordered subset of the poset. So each flag of P has length n+1. It contains exactly n+2 faces, including the least face and the greatest face. So to illustrate, okay, in the triangle, yung ating partially ordered set, yung diagram for the triangle, the least face is the null set. The greatest face is ABC. Each flag has length 3. So you go from here. This is 1, 2, 3. So lahat ng flags may length 3. You can check that for all the other possible chains. Now, we shall say, because each flag has length 3, we can then associate a natural rank to each kind of face depending on the distance from the null set. So the first, the faces that are immediately adjacent to the null set itself is a face with rank. We say that it has rank -1. Yung first level, yung vertices, we consider these as faces with rank 0. Yung edges natin will be faces with rank 1. And yung triangle natin will be a face of rank 2. So this is also our F2. Another term for a face of rank I is an I face. So there is a third condition that we want to satisfy in order for our poset to be a polytope. This is a little bit more complicated than the first two. I-try nating i-illustrate para maintindihan natin. So for any 2 distinct flags, phi and psi, we can find a sequence of flags. So phi naught is the first flag phi. And then we have phi1 up to phi sub k -1. And then phi sub k is the flag psi. So ano ang gusto nating masatisfy nitong sequence na to? First, each flag phi sub j, for j from 1 to k, must contain all of the faces common to phi and psi. Second, any 2 consecutive flags in the sequence must differ in exactly 1 face. So, medyo complicated siya. Let's illustrate that. Let us look at the triangle again, the poset for the triangle. Let us look at the flag phi consisting of the null set, the vertex A, the edge AB, and the triangle ABC. And let us look at the flag consisting of the null set, the vertex C, the edge BC, and the triangle ABC. So let's take as our phi1 the flag with elements phi, b, ab, and abc. Now, if we compare this flag with the flag phi, this contains the null set and ABC. And etong dalawang faces na yan, yung least face and the largest face, those are precisely the faces in the intersection that are common to phi and to psi. So this flag contains the intersection of phi and psi. Okay. Next, it differs from phi in exactly one face. Nag-differ lang siya doon sa vertex. Okay. Now, if we take phi sub 2 to be this face, so ang elements niya ay yung null set, yung vertex B, yung edge BC, and yung face, yung triangle ABC. So again, this contains phi and ABC. That's the intersection of phi and psi. And this differs from phi subscript 1 in exactly one face. Nagdi-differ lang siya doon sa edges, doon sa edge, okay? Pero for these other elements, pareho sila, nag-intersect sila. Now, compare phi 2 with psi. So, they contain the intersection of phi and psi, and they also differ in exactly one face, which is yung ating doon sa vertices. So what do we have? Meron tayong sequence of faces, or of flags rather, which satisfy the definition, which satisfy the condition stated here in P3. Okay? So, anong gusto natin? Gusto natin magawa natin yan for any two flags that we choose inside this diagram. So, that is condition P3. Another way of, yung condition P3, the condition that is described in P3 is also called strong flag connectedness. So any poset which satisfies P3 is said to be strongly flag connected. Now there is a fourth condition, a last condition that must be satisfied, and it is that for any I from 0 to n-1, okay, if we take any I-1 face fi minus 1 and any I plus 1 face f sub I plus 1, such that f sub I minus 1 is incident to f sub I plus 1, so may chain na nagko-contain sa kanilang dalawa, then there should be exactly two I faces such that f sub I is adjacent to f sub I minus 1 and to f sub I plus 1. Ito rin yung tinatawag na diamond condition. So, anong itsura nun? So, kung ito yung diagram natin, ito si f sub I plus 1, ito si f sub I minus 1. Yan, may dalawang, ito ay rank I plus 1, ito ay rank I minus 1. So, dapat may exactly dalawang rank I faces adjacent to both of them. We can just show na by inspection, the diamond condition is satisfied by the diagram for the triangle, by the partially ordered set associated with our triangle. So if you take any two, say itong ABC and B, so faces sila, of course, B is incident with ABC. There are exactly two edges. Okay, so this is rank 1, this is rank 0, this is rank 2. May dalawang rank 1 faces, these are AB and BC, which are incident to both. And you can check that for any pair of faces, incident faces whose ranks differ by 2. So the poset for the triangle is satisfies the all of the conditions that we need for an abstract polytope. Okay. this is therefore our conclusion is that this diagram represents an abstract polytope of rank 2 or a 2 polytope. So we are interested in symmetries of abstract polytopes. A symmetry of an abstract polytope P. Okay, so again, ano ang polytope? This is a partially ordered set whose elements are called faces. A symmetry is a permutation of the set of faces of the polytope, so yung points doon sa ating diagram, that preserves incidence. That is, whenever we take two faces F and F prime, if F is incident, so F is incident to F prime if and only if the image of F under the permutation is also incident to the image of F prime under the permutation. One implication of this condition is that the rank of F will be equal to the rank of phi of F. So this is a face, this is another face, they would have the same rank. So pinapermute ng phi yung faces of the same rank. The set of all symmetries of a polytope forms a group called the automorphism group of P. It turns out that the automorphism group can be represented as a permutation group on faces of a fixed rank. So in particular, the automorphism group can be represented as a permutation group on the vertices of our polytope, or on the, one faces, or so this should be zero faces, the zero faces of our polytope. To illustrate, so let's look at again at our yung ating abstract polytope derived from the triangle. Kunin natin yung permutation phi of the face set which swaps the vertices A and B. So this sends A to B and B to A. Now what happens to our edge AC? Yung edge AC ay mapupunta sa edge BC, and then yung edge BC becomes the edge AC. That's what happens when A and B are swapped. Now all of the other faces will be fixed. Kasi if you swap A and B, then the edge AB is still the edge AB. The triangle ABC is still the triangle ABC. The edge C, the vertex C is unaffected also. It's easy to see that any permutation of the three elements of the three vertices corresponds to a permutation to an automorphism of the polytope. So the automorphism group of this polytope is isomorphic to the symmetric group on three letters. Also, any such permutation will induce a permutation of the flags, of the maximal chains of our polytope. So for instance, the flag, this flag, yung may elements na null set A, AB, ABC. Under this permutation, if you swap A and B, then the vertex, the null set and ABC are fixed. The vertex A becomes B, and then AB remains. So yung flag na to, this flag, is sent to this flag, and vice versa. Okay. The flag with elements phi, A, AC, ABC is swapped with the flag phi, B, BC, and ABC. And the flag phi, C, AC, ABC is swapped with phi, C, BC, ABC. So, nag-i-induce tayo ng permutation din ng flags. Okay. Now, we say that a polytope is regular exactly when the automorphism group is flag transitive. So, pag tinignan natin yung action induced by the automorphism group on the set of flags, ibig sabihin, for any two flags, phi and psi, we must always be able to find a permutation row, an automorphism row of the polytope, which sends the flag phi to the flag psi. So that's what is meant by flag transitive. So we now have our full definition of abstract regular polytopes. This is a partially ordered set satisfying the 4 conditions P1 up to P4 and whose automorphism group is transitive on flags. So, for instance, yung polytope natin derived from our triangle, okay? Yung ating automorphism group, which is isomorphic to S3, it is easy to show by inspection that this is transitive on the flags of the polytope. Therefore, this is an abstract regular polytope of rank 2. Okay, now let us suppose that in our polytope, let's go back to the general case, we have a polytope of rank n. Let us take a flag, let us fix a flag phi with faces f -1, so ito you see null set, f0, and so on up to fn. For any I from 1 to n-1, we shall take rho sub I, okay? Sorry, we are assuming here that our polytope is regular. So transitive tayo on flags. Let's take rho sub I to be the automorphism which sends phi to the flag psi sub I. Now, ano yung psi sub I? Psi sub I is the unique flag which differs from phi in the face of rank I. So, by the diamond condition, yung condition P4 dun sa definition ng abstract polytope, this flag is unique. May isang flag lang which will differ, which coincides with phi in all other faces except for the face of rank I. So, and dahil ang ating polytope ay regular, meron tayong automorphism which sends phi to that flag psi sub I. So, yun ang definition natin ng notation ng rho sub I. Now, these rho sub I's will be important. These are all, it's easy to see that these are all involutions. Or it can be shown that these are all involutions. And also, it is possible to show that the full automorphism group of P is generated by these involutions rho sub I. Now, sorry, these are theorems. These are established results. Apart from that, we can also show that that the automorphism group of our abstract regular polytope, which has these permutations as generators, satisfies 3 conditions C1, C2, and C3. First condition, the product for any I and j from 0 to n-1, the product of any 2 of these maps raised to some integer p sub ij is equal to 1. If I and j are equal, then that is this pii is equal to 1. If I is not equal to j, then this is greater than 1. In particular, this is 2 whenever I and j differ by at least 2. If I and j are consecutive, so let's say j is I plus 1, then yung pij natin can be any integer greater than or equal to 2. So it's possible for that to be greater than 2. And then we have an intersection condition, C3. If we take 2 subsets, capital I and capital J of our index set, then if you take the subgroup generated by the rho sub I's for small I in capital I, and the subgroup generated by the rho sub J's for J in capital J, take their intersection, we shall get the subgroup generated by the rho sub I's where I is in capital I intersection capital J. Now, any group which is generated by maps of this form and which satisfies C1, C2, and C3 is called a string C group. what is the connection between string C groups and abstract regular polytopes. So yung previous remarks natin show that the automorphism group of an abstract regular polytope is a string C group. We can turn that question, that concept around and ask, suppose we start with a string C group gamma. Is it possible to find an abstract regular polytope P whose automorphism group is that string C group gamma? This question has already been answered, and the answer is yes, it is possible to find such a polytope. We shall not show the details of the construction, but the idea behind this construction is we shall take as the faces of the polytope cosets of certain subgroups of the string C group. Now, what is the specific problem that we worked on? So the general problem is, suppose we are given a group G, any finite group G. Can we find an abstract regular polytope having G as a subgroup of automorphisms? Because of the previous established connection between string C groups and abstract regular polytopes, the answer here will be yes if we can represent G as a string C group. So bakit? Kasi sabi natin, any string, if you have any string C group, you can construct a polytope having that group as a group of automorphisms. So all we need to do is to work with the group itself and see if we can find generators row 1, row 0, row 1 up to row sub n minus 1, satisfying the three conditions in the definition of string C groups. Now, this has been explored and verified for certain groups, such as the symmetric and alternating groups. May mga lower bounds for n that has been established. Now, they have a string C group representation, and therefore there exist polytopes, abstract regular polytopes, admitting these as automorphism groups. This has also been verified for orthogonal groups with dimension D over fields of even characteristic, finite fields of even characteristic. There also for orthogonal groups over field of odd characteristic, but for this case, the dimension has to be odd. I'll explain this part more in a bit. Also for symplectic groups over fields of finite of even characteristic, and some of the other projective groups, projective special linear group at saka projective symplectic group. Now, this one is, I only learned this result, this part, the highlighted result, last week when I was preparing for this talk. It turns out that some of the problems that Michael and I were working on would have been covered by these results. I'm not sure if this has been established for all orthogonal groups of odd dimension, but at least for some, my results na may extend to to these cases. What I will present, as I said, has been in hiatus since 2019. So may overlap ng konti dito sa case na to na meron ng result. But I will show it nonetheless kasi yun yung starting point namin, hoping for to be able to tackle the more general case, which is, well, the remaining open cases, orthogonal groups with even dimension over fields of odd characteristic. So, ano yung orthogonal group? Okay, the orthogonal group has a definition na geometric, but I will describe this more as matrices. We start with a vector space V of dimension n over a finite field FQ. Take a fixed ordered basis with elements small v1 up to small vn. We suppose we have a quadratic form Q on V. So ano ang quadratic form? This is a mapping from V to FQ, such that for any scalar lambda, Q of and any vector V, Q of lambda times V is equal to lambda squared times Q of V. If you have such a quadratic form, we can obtain an associated symmetric bilinear form, B. So this is a map from ordered pairs of vectors to the underlying field, satisfying the condition that B of UV is equal to Q of U plus V minus Q of U minus Q of V. We can represent this bilinear form as a matrix with respect to our fixed ordered basis V1 up to Vn. The orthogonal group on V, also denoted as O of n comma Q, consists of all invertible n by n matrices over Fq, satisfying the condition that G times B times G transpose is equal to B. So this is the orthogonal group corresponding to the bilinear form B. Now, so these are some of our partial results. So again, ano yung goal natin? Our goal is to find generators of the orthogonal group of this group O of NQ, satisfying conditions C1 up to C3 in the definition of string C group. That's it. Once we are able to verify that those conditions, then it's immediate na yung conclusion na there is a polytope, an abstract regular polytope, admitting our orthogonal group as a group of automorphisms. Now, we were able to do that successfully for n equals 3. So here, our characteristic is odd because that's the remaining open case. We take omega to be a primitive element of FQ. So we write our generators as matrices, 3 by 3 matrices. We have R of, well, there's a reason for this notation, R of 3, 0, R of 3, 1, and R of 3, 2. Let's take G superscript 3 to be the group generated by these 3 matrices. I will not show the details, but we were able to establish that this group does indeed generate the full orthogonal group of dimension 3 over FQ. And moreover, this group satisfies all of the necessary conditions for a string C group. So this will give us that result means that the orthogonal group of dimension 3 over a field of odd characteristic is indeed an automorphism group of some abstract regular polytope. So what we want to do is to take this representation and see if we can generalize that to arbitrary dimension greater than 3. Here is what we are attempting. So here we are still in odd characteristic. Omega is still a primitive element of FQ. What we do is, so we define these larger matrices. Rn0 is this matrix. So anong kinalaman niya doon sa first, you can see medyo may binibuild natin siya from R3, these original matrices. So you can see here an R30 and then dugtungan lang natin ng identity matrix. And yung Rn n-1, ilagay natin dito yung R32 sa lower right corner and then dugtungan lang natin ng identity matrix and 0 everywhere else. And for I from 1 to n-2, this is our R subscript n comma I. So what do we have? May R31 tayo sa gitna. And then dugtungan lang ng identity matrices on the remaining parts of the diagonal. Now, this is where our work stopped. Unfortunately, so we were able to show that the group generated by these matrices satisfies conditions C1 and C2 of the definition of string C group. Well, we are attempting this for the general case, so open problem pa. Does this satisfy condition C3? Condition C3 is not that easy to verify. Ito yung weird na intersection condition. Also, this is not so simple and might involve medyo madugong group theory na arguments. Is this the full orthogonal group? So that's still, we were not able to establish that. What we were able to establish is for this question, the second question, we showed that this does indeed preserve a symmetric bilinear form on V. So the most that we can say is that this is a subgroup of the orthogonal group. And that this is irreducible, that is, it does not leave any invariant non-trivial proper subspace of V. Pero hindi pa namin na-establish yung equality. And also this part. So that's where we stopped because I had to go back to Manila. And that is also the remaining open problem. Of course, more general open problems. I think medyo konti pa lang yung results here. So what about other groups? Can you also show, can you also find a string C group representation for other kinds of groups? And so can other kinds of groups also be admitted as automorphism groups of abstract regular polytopes? And that is the end of my talk. Thank you very much for your attention.
Thank you very much, Dr. Amara, for your talk. Can you all please give Dr. Amara a round of virtual applause? Thank you. So I was not able to mention earlier that she's she's currently in the University of Western Australia on a postdoctoral position. So do we have any question from the audience? So you can type it in the chat box, or you can unmute yourself. You can also raise your hand and unmute yourself if you have any question. Question here in the chat box, may relationship po ba sila sa Cayley graphs and groups?
Wala. Parang wala. Well, groups definitely kasi you are working with the groups na. So parang yung from abstract polytopes, you na-convert na siya to a problem of representing a group as a string C group. So in fact, puro group theory na to.
Okay. Another question here. Ano yung hindi ma-extend sa dimension n equals 3 para ma-prove yung condition C3?
Okay. Can I stop sharing? I-check ko lang yung notes ko. So for that, I think nagiging complicated yung merong part na nagiging complicated eh. Yung yeah. Parang dahil mas malaki yung dimension, nagkakaroon ng mas maraming cases dun sa argument. So parang kung sa dimension 3 lang, parang may, I think it's the intersection condition. Tsaka yung madaling i-verify yung intersection condition. Pero I think medyo ad hoc yata yung methods na nag-work lang siya for the small dimension. Tapos yung pagpapakita rin ng orthogonal groups, meron ding may pagka-ad hoc din na dahil maliit lang yung dimension, parang madaling makover lahat ng cases. So, yeah, madali i-conclude na full orthogonal group siya. Whereas kapag lumalaki na yung dimension, even for dimension 4, nahirapan kami. Parang, gusto namin ipakita na yung smaller subgroups will also be string C groups. Parang may ganong part sa argument na if you can show that this smaller subgroup is a string C group, then well, ano ngayon? Yung gusto namin yung intersection nun ay maging specific subgroup, pero yeah, basta gumugulo yung, dumadami yung cases, gumugulo yung argument. Basically, kapag malaki, parang ang laki kasi ng group, so hindi siya basta-bastang, hindi lumalabas kaagad yung conclusion. Parang ganon. And at least at that time, hindi ko mag-grasp yung underlying geometry. So, and unfortunately, I was not able to go back to that since. Yeah, sorry if I can't answer it in a clear as clear a way as I could, because I would be happy to discuss this offline in more detail kasi yeah, medyo magulo siya. Medyo magulo pa yung very unfinished work nga siya. So magulo yung mga arguments.
Okay. So well, hopefully you'll be able to gather again your ideas.
Sana.
So, I have a question here sa direct message. Ayan, so meron tayo anonymous sa question. I don't know if possible din ba na may combinatorial problems out of this. Lately lang din ako na-introduce to abstract polytopes through Dr. Velasquez. So are there combinatorial, can you think of at the moment? Or
hindi ko alam kasi yun din ang experience ko rin sa
okay. So nawala po ba si Dr. Amara? Carmen, if you're still there, pakigalaw po ang baso. Okay. And so actually, she was supposed to be the first speaker for this session, pero meron atang power issues doon sa area na kung nasaan sila. And kaya po muna si Mr. Santa Ana, but anyway, I think I don't know kung ayan. So baka hindi na tayo nagkaroon hindi na siya makabalik. But anyway, okay, so if you have other questions, I think we can forward that to Dr. Amara. You can also find her email address doon sa Institute of Mathematics, sa official webpage ng Institute of Mathematics. And so ito rin naman po, itong webinar natin is also on the IMath Facebook page. So, ayan. So you can also go back to it. So makikita nyo rin dito yung mga open problems. So if you have any ideas or any input, so maybe you can also share and maybe have some collaboration. Okay, so ayan po. So maybe we'll end our webinar here. So thank you very much to all those who attended. And thank you to our speakers, Jomar Kevin Santa Ana and Carmen Amara, sa pagpapaunlak po at pag-share ng kanilang naigawa. Okay, and please visit the official IMath Facebook page for any updates dun po sa mga susunod nating webinar. Okay, so again, thank you very much and have a nice week ahead. Thank you.
Thank you. Same to you.
Thank you po, sir. Thank you po sa inyo lahat.
Thank you again, Kevin. So may question dito na evaluation. Wala tayong evaluation dito. But, okay, so again, thank you. I will end this now. Goodbye.